Welcome to our lecture on kinematics in mechanical engineering. Today, we'll dive into the fascinating study of motion without considering the forces causing it. Kinematics is a cornerstone of mechanical engineering, offering foundational principles to analyze and design a wide array of mechanical systems. By understanding how objects move, we can predict and control the behavior of machines and structures. In this video, we will explore various kinematic principles and their applications. You'll gain insights into different types of motion, from linear to angular, and learn how to describe these motions using mathematical equations. We'll also showcase real-world examples demonstrating how kinematics solves engineering challenges, such as the motion of pistons in engines and the trajectory of robotic arms. Stay engaged as we embark on this educational journey into the world of kinematics, setting the stage for deeper exploration into the mechanics of motion. You'll see just how integral these principles are to mechanical engineering. Welcome to our in-depth exploration of kinematics in mechanical engineering. In this initial segment, we'll dive into the core concepts of motion. Motion can be classified into various types, each essential for understanding mechanical systems. We'll begin with linear motion, where an object moves along a straight path, such as a car traveling down a road. Next, we'll examine angular motion, typified by rotation around a fixed point, like a spinning wheel. Understanding these fundamental types is crucial as they form the basis for analyzing more complex systems, whether it's the predictability of a moving part or the efficiency of an entire machine. By grasping these concepts, we equip ourselves with the tools needed to tackle real-world engineering problems. Now, let's embark on this journey, starting with the building blocks of motion that underpin mechanical engineering. Stay tuned as we bring these principles to life with practical examples and detailed explanations. Understanding motion is crucial for analyzing mechanical systems in kinematics. Often, we encounter problems requiring in-depth analysis to find solutions. Today, we'll dive into one such problem common in engineering. A significant challenge in kinematics is determining the motion of objects within various mechanical systems. This isn't just about tracking movement, but interpreting behaviors and predicting future states. Let's consider a scenario many of you might encounter in your careers. Imagine analyzing the motion of a component within a complex system, such as a piston in an engine. This requires a comprehensive understanding of kinematic principles for accurate analysis. Detailed analysis is essential because without it, predicting motion and ensuring mechanical systems' efficient operation would be nearly impossible. As we continue, you'll see how this scenario sets the stage for applying fundamental kinematic equations and concepts. Next, we'll delve into the equations that allow us to model and resolve these motion challenges effectively. To solve kinematic problems, we rely on fundamental equations. These kinematic equations form the backbone of motion analysis in mechanical systems. They help us describe the motion of objects mathematically, breaking down complex movements into understandable components. First, we consider the basic equations: velocity, acceleration, displacement, and time. Each of these parameters relates to one another through specific mathematical forms. For instance, the equation of motion, v equals u plus at, helps calculate the final velocity v of an object given its initial velocity u, acceleration a, and time t. Next, let's derive these equations and see their practical applications. The derivations give us insights into how motion parameters influence each other under different conditions. Understanding the origin and interrelation of these equations is crucial for accurate problem solving. To illustrate, we'll walk through example calculations. Imagine a car accelerating from a stoplight. Using our kinematic tools, we can predict its velocity at any time and the distance it covers. Such calculations aren't just academic, they're vital in designing and analyzing real-world engineering systems. As we move forward, you'll see how these equations integrate with more complex principles, building a robust framework for kinematic analysis. Position, velocity, and acceleration are foundational parameters in kinematics. Let's explore what they mean and how they relate to each other. Position is simply where an object is located, like coordinates on a map. Velocity builds on this concept, describing how quickly an object moves and in what direction. Imagine driving a car. Your speedometer shows velocity. Acceleration, on the other hand, tells us how the velocity changes over time. If you press the gas pedal and the car speeds up, that's acceleration. These parameters are deeply interconnected. Position helps us determine velocity, as velocity is the rate of change of position. Similarly, acceleration is the rate of change of velocity. To visualize these relationships, we often use graphs. A position time graph shows how position changes over time. The slope of this graph represents velocity. Meanwhile, a velocity time graph illustrates changes in velocity, and its slope shows acceleration. Understanding these graphs and the relationships between position, velocity, and acceleration is crucial for analyzing motion. As we move forward, you'll see how these principles apply to real-world engineering problems, making them an essential part of a mechanical engineer's toolkit. Let's apply the kinematic principles we've learned to analyze the motion of a piston in an engine. First, we'll consider a real-world example where understanding piston motion is crucial for engine efficiency. Next, we'll apply the fundamental kinematic principles we've discussed. Our approach involves examining the piston's position, velocity, and acceleration throughout its cycle. We'll identify the kinematic equations that describe this motion and then break down the problem step by step. We'll calculate the piston's position at various points in the cycle, followed by determining its velocity and acceleration. This methodical analysis highlights the importance of kinematic principles in practical mechanical engineering problems. As we move forward, you'll see how these principles are crucial for ensuring the smooth operation of an engine. In this segment, we'll dive into the graphical methods used in kinematics. Graphical analysis techniques are invaluable for visualizing and interpreting motion, helping us see the relationships between velocity, acceleration, and time clearly. When analyzing motion, we often rely on velocity time and acceleration time graphs. Each graph type presents unique insights, enabling us to decipher motion's characteristics. Velocity time graphs show how an object's speed changes over time. From these graphs, we can determine acceleration and even calculate displacement by looking at the area under the curve. Acceleration time graphs, on the other hand, reveal how the rate of acceleration varies. These are particularly useful for understanding changes that aren't constant, helping us predict future motion. Interpreting these graphs accurately is key to solving many kinematic problems. By mastering these techniques, you'll gain a powerful toolset for analyzing complex motion scenarios. Next, we'll explore advanced kinematic concepts that build on these foundations, integrating these graphical methods with more sophisticated analyses. Beyond the basics, kinematics delves into advanced concepts vital for intricate motion analysis. At the forefront of this exploration is relative motion, which deals with understanding the motion of objects from different reference points. Another critical idea is the instantaneous center of rotation, allowing us to determine the specific point where an object appears to be rotating at any given moment. These concepts are particularly crucial in complex motion analysis, where simple equations fall short. By comprehending these advanced topics, engineers can predict and analyze the movement of interconnected components with higher accuracy. As we delve further, you will encounter the applications of these principles in real-world engineering scenarios. Stay tuned to uncover how these advanced kinematic concepts translate into practical solutions that drive innovation in mechanical systems. Let's move forward to explore their implications and applications in greater depth. Kinematics is not just a theoretical concept, it has profound practical applications in engineering. From the design of intricate machinery to the detailed analysis of mechanical systems, understanding motion is paramount. Engineers leverage kinematics to refine automotive designs, ensuring vehicles function smoothly and efficiently. In robotics, kinematics underpins the development of precise and agile movements, enabling robots to perform complex tasks. Moreover, in manufacturing, it aids in the optimization of production processes, enhancing both speed and precision. These real-world examples underscore how vital kinematics is to engineering, influencing everything from the smallest components to the largest systems. As we move forward, you'll see how these principles apply across various engineering domains and contribute to innovation and advancement in the field. In this video, we've explored the fundamental principles of kinematics. Throughout our journey, we defined motion without considering forces, examined types of motion, and analyzed real world problems to solve using kinematic principles. We uncovered how kinematic equations, the relationships between position, velocity, and acceleration, and graphical methods help us understand and depict motion precisely. Moreover, by studying practical applications and advanced concepts, we saw how kinematics plays a crucial role in engineering, from robotics to automotive design. Understanding these concepts is more than an academic exercise. They are critical for any mechanical engineer striving to design, analyze, and optimize mechanical systems. Kinematics forms the backbone of much of the mechanical world, enabling us to predict and control how systems behave. As we conclude, we encourage you to delve deeper into kinematics. Continue exploring, questioning, and applying these principles in your engineering endeavors. Whether in academia or industry, mastering kinematics will be a powerful tool in your professional toolkit. Thank you for joining us on this insightful journey into the fascinating world of kinematics.